we are going over the OCR Chemistry AS level 2020 paper, Breadth in Chemistry, and we are doing section A. Okay, so which substance contains polar molecules? So these are the four options we are giving, and whenever you hear the word polar, you should think of NOF. That's nitrogen, oxygen, or fluorine. If a molecule contains one of these atoms, then there's a chance that it will be polar, and so that would mean that A is the wrong answer, because it does not contain nitrogen, oxygen, or fluorine. We can also think of it as like dissolves like, so polar substances will dissolve in, polar molecules will dissolve in polar substances. We know that water is a polar substance, and so C2HF will not dissolve in water, therefore it cannot be polar. Another way you can do this is by drawing the shape of the molecules, because symmetrical shapes are not polar. So carbon dioxide, if we draw it over here, yes, it contains the oxygens with the lone pairs. However, it's a symmetrical shape, and so it will not be polar. And so that cancels carbon dioxide. Now, if we go to SF6, the fluorines contain the lone pairs. However, once again, it's symmetrical. And so D is the wrong answer. If we go to NCl3, we can see that the shape is not symmetrical. There is a lone pair from the nitrogen, and that will be giving the polarity. And so C is the correct answer. Right, question number 2. What is the formula of silver carbonate? Okay, so we know that silver is Ag and carbonate is CO3 2 minus. And silver is Ag plus. There's a +1 charge, it's a metal. And carbonate is CO3 2 minus. What we can do is we can write them side by side and then cross them. What that means is we cross the charges. So Ag is +1, therefore we drag the 1 to the other side, and so it'll be CO3 minus CO3 only. And the CO3 2 minus, 2 is dragged to the other side, and so Ag becomes 2. And so we have Ag2 CO3. And so that's a good way to determine formulas when they've given you, silver and carbonate, and you just cross them over. So you can do this with any example. Another way you can do this is by using the charges as well, but you would see that silver is a +1 charge, whereas the carbonate is a 2 minus charge, and therefore you would need 2 lots of silvers to become 2 plus to cancel out the charge from the carbonate, and so you get Ag2 CO3. And so that would mean that the answer is also C. Which statement explains why ice is less dense than water? So when we mean less dense, it means lighter. More dense is heavier. And so let's see. Hydrogen bonds are stronger in ice than in water? No, because hydrogen bonds is one type of bond, and they'll have the exact same strength in every single molecule they're in. It's the number of hydrogen bonds present that determines the strength of the molecule, not the actual hydrogen bond. So A is wrong. Hydrogen bonds hold H2O molecules apart in ice. That would make sense, because the further apart that they're held, the less dense ice becomes. And so what that means is basically we have this hydrogen bond here, and that happens between water. In oxygen, this is just further apart. So as opposed to it being over here, then it can stretch all the way over here, and we have a water molecule over here. So it just means that the hydrogen bonds are further apart from each other. And that is why ice is less dense. So that's the correct answer. So C, ice is a solid, but water is a liquid. That's facts, yes. But it does not explain why ice is less dense. Ice contains hydrogen bonds, but water does not contain hydrogen bonds. Well, that's false, because we know that water contains hydrogen bonds and ice is water. It's just frozen water. And so if ice contains hydrogen bonds, then water must contain hydrogen bonds. And that's why the answer is B. Some group 2 compounds can be used to neutralize acid soils and to treat indigestion. Indigestion is just heartburn. Which group 2 compound would not be suitable for either use? Okay, so when we hear the word acid and we hear the word neutralization, they want to know that which 2 compound which would be able to neutralize the acid. And so we know that if we scroll through the list, barium sulfate is a sulfate, calcium carbonate is a carbonate, and carbonates react with acids. And therefore it will neutralize the acid and also form carbon dioxide and water. calcium hydroxide is a hydroxide. A hydroxide is a base, and also so it's an alkali. An alkali reacts with acids in a neutralization reaction. Magnesium hydroxide is a hydroxide, again a base, so an alkali, and so will neutralize acid. So all these three are correct, meaning that barium sulfate won't react with an acid to neutralize it, and therefore the answer is A. Which p block elements contains atoms with one unpaired electron? Okay, so the p block on the periodic table is group 4, 5, and 6, and they're called the p block because their last electron is in the p shell orbitals. So remember, in orbitals we have s, p, d, and f. So the p block would mean that the outer electrons would be in the p shell orbital. And so aluminium, if we draw it out, we would have its last electron in the p orbital. A silicon would have its last 2 electrons in the orbital, and phosphorus would have 3 electrons in the 3p orbital, and sulfur would have 4 electrons in the 3p orbital. So all the electrons are on the p orbitals. However, this is asking for one unpaired electron. That means only one electron on its own in the p orbital, and we can see here that only aluminium will possess one electron in the p orbital. Yeah? And that's why the answer is A. Which equation for a redox reaction is shown below? Oh, sorry, the equation for a redox reaction is shown below. So this is the equation. Which statement is correct? Okay, so this is about oxidation and reduction, and we need to see, is chlorine undergoing oxidation and reduction, or is it only being oxidized and oxygen is being reduced, or is it oxygen is being oxidized and reduced, or oxygen is oxidized and chlorine is reduced? Right, so we'll write it out. And this is about oxidation numbers. So if we so oxygen is -2, we have 3 lots of oxygen, it's -6, and hydrogen is +1, and so that would make chlorine +5. And chlorine HCl will be -1 because hydrogen is always +1. And in the products we have -2, and there's 2 lots of oxygen, so -4, meaning chlorine is +4. And chlorine on its own, so anything when it's on its own, so as an atom on its own, so an element, will be 0. And we have H2O, oxygen is -2, and we have hydrogen, which is +1, 2 lots of hydrogens, +2. Now let's write them out. That means we had chlorine going from a +5 to a 0. And therefore it's gained electrons, and therefore it's been reduced. We also have chlorine going from -1 to +4 over here. Therefore it's lost electrons, and therefore it's been oxidized. Therefore chlorine has been both oxidized and reduced, and that's why the answer is A. But let's go through the oxygen as well. So oxygen we have -6. We only have oxygen on this side of the reactants, and we have -6. We then see that oxygen becomes a -4, and that means it has lost electrons, and so that's oxidation. We also have oxygen over here, and it's a -2. That means oxygen started off as a -6 and became -2. That also means it's lost electrons and therefore it's undergone oxidation. Therefore, in no way did oxygen become reduced or oxidized and reduced at the same time, and so therefore A is correct. It's the more accurate one than D as well. Potassium ferrite contains 2 potassium ions for every ferrate ion. What is the formula of the ferrate ion? Okay, so as you can see, we have Roman numeral over here, and I've written out over here. So V and I would be 6. Yeah, and so that means that the oxidation charge on the ferrate ion would be a +6. And that would go for the ion, because if we see this is the ferrate ion, and if we write down the oxidation state, it tells us that for 2 potassiums, we have 1 ferrate ion. So potassium is +1, and we've got 2 potassiums, and therefore becomes +2. Oxygen on its own is -2, but because the charge over here is a +6, and they must be equal to each other, then oxygen must be -6. However, since we know that oxygen exists as -2 only, then we must have had 3 oxygens to give us a total of -6 charge. And so this comes up with K2FeO3. By the way, here they've just removed the potassium. So if you remove 2 plus charges of potassium, you get a -2. And so that's why people would go, well, it's FeO3. Well, there's one step that's missing. If you then look at the oxidation numbers again, so we have -6, but we have the +2, that gives us iron with a +4 charge. We need iron to be a +6 charge as written over here. The only way we can get iron as a +6 charge is to increase oxygen to 4, because that would mean that oxygen will have a -8 charge plus the 2 potassiums a +2 charge. This leaves us with a +6 charge for iron. And if we then remove the +2 charge, we get a -2 charge, sorry, 2 minus charge over here, and that would mean that the answer is B. So, number 8. What is the unbalanced equation for the reaction of copper with concentrated nitric acid is shown below. What is the number of moles of HNO3, so nitric acid, that react with 1 mole of copper? Right, so the first thing you do is you write the equation, and then you write how many atoms are present in each side. So copper, we've got 1 and 1, hydrogen, we've got 1 and a total of 2. Nitrogen, we have 1, and here we've got a total of 3 nitrogens. Oxygen, we've got 3, and oxygen, we have 9. So, starting with that, we can see that our oxygens are not balanced. Yeah, we have 9 on this side, and we only have 3 on this side. So our first instinct is to put 3 over here, because that would mean we have 9 oxygens now. However, that's going to have effect on the other atoms. That would also mean that we have a total of 3 hydrogens here and only 2 hydrogens here. So we're going to have to increase the hydrogens. We also have 3 nitrogens here, and we also have 3 nitrogens here. So okay, that's fine. But the oxygen is a problem. We have 3 here and only 2 here. So what we're going to do is we're going to put 2 here. However, now that would mean that we have 4 oxygens here and 10 oxygens here, whereas here we only have 9 oxygens and now 3 hydrogens. So what we're going to do is we're going to remove the 3 and put the 4, because that restores the number of hydrogens to 4, and that means both hydrogens on the side are equal. Now, let's see the effect on the other atoms. Nitrogen, we have 4 in total. We only have 3 nitrogens here. We have 2 over here and 1 over here, so we need 4. So we're going to put a 2 up front. That's going to change the number to 4. So now we have 4 hydrogens on this side and 4 on both sides, and 4 nitrogens on both sides as well. Now, the oxygens, let's see how that changed. The number of total oxygens here is 12. Now, how many oxygens do we have here? We have 2, we have 4, so that's 6, and now we have 6, and a total of 6, that gives us 12. So everything is balanced. And so that would mean the total number of moles for HNO3 is 4, and that would mean that the answer is C. Right. 2 decimeters cubed of chloride of Cl2 gas reacts with 2 decimeters cubed of ClF3 gas to form 6 decimeters cubed of gaseous compound. The reaction has 100% atom economy and all volumes are measured at the same temperature and pressure. What is the molecular formula of the compound formed? Right. So when they say 100% atom economy, that means there's only one product being formed. And so let's write it down. We have Cl2, and we've got 2 decimeters cubed of that. We have ClF3, and we have 2 decimeters cubed. And we have one product. Yeah? That's being formed, and it tells us it's 6 decimeters cubed. So, and they want us to work out the molecular formula of the compound, the product that's formed. So it's 100% one product. Let's add up what we have in the reactant. So we have 3 lots of chlorines and 3 lots of fluorines. And we need to have one product that's equal. And since we have it 6 decimeters cubed from 2 decimeters cubed, we had to have times it by 3. Therefore, we've had to have 3 moles of the product. So that means this number is 3. 3 times 2 is 6. Therefore, we need to split the product 3 ways. And if we have Cl3 and F3, therefore, if we split that 3 ways, we have ClF for each product formed. So ClF plus ClF plus ClF will give us 3 lots of ClF products. That's why the answer is A, because we needed to have a ratio of 3. And if we have a total of 3 chlorines with 3 fluorines, that means each product will have 1 chlorine and 1 fluorine. Which sample contains the greatest number of molecules? Okay, so molecules is Avogadro's times moles, and moles is mass over mR. So we have the mass, and we can work out the the mR. Therefore, we can work out the moles. So that's 1 over 32, gives us 0.03 for moles. And we times it by Avogadro, which is 6.02 times 10 to the power of 23, which gives us 1.88 times 10 to the power of 22. We do this with B as well. We calculate the moles, and from the moles we times Avogadro, and we get 2.617 times 10 to the power of 22. Same thing with number 3. We work out the moles, and from the moles we get, we times it by the Avogadros, and we get 1.456 times 10 to the power of 22. We do this with D. We work out the moles, and we times it by Avogadro, giving us 9.49 times 10 to the power of 21. Therefore, the greatest number of molecules is from B. And that's the answer. Hydrogen and oxygen react as shown below. Yeah. What is the bond enthalpy for the OH bond? Okay. So let's draw out what we have. So we have 2 lots of H2 bonded. So this is what H2 looks like, and we have 2 lots of that. We also have 1 lot of O bonded to O, and that gives us H2O, but we've got 2 lots of H2Os. And they want us to work out this bond. Now, we have a total of 4 OH bonds. We have this one, that one, that one, and that one. Yeah? So, let's see what we have as well in terms of the numbers, so bond enthalpies. So we have 4, 3, 6 for 1 H bond, and we have 2, so we're going to times that by 2, and we have 1 O bond to O, and so that's plus 498. We add them together, we get minus 1370. Oh, sorry, we have 1370. That's not a minus, that's equals to 1370. And we have the OH bonds. That's all we have. But we know we have the total enthalpy, which is minus 486. So we write down this equation, which is the answer, and you get that by doing reactants minus products. So we have minus 483 equals reactants minus products. We have the reactants, so it becomes minus 48. Sorry, why am I getting 43? Minus 486 equals the products minus. Minus 486 equals reactants minus products. We have the reactants, it's 1370, so we substitute it in, so we get minus 486 equals 1370 minus the products. So we want to get the product, so we're going to take the 1370 to the other side, and because this is a plus, we take it to the other side, and so it becomes negative. So minus 486 minus 1370 will give us the product. However, note that the minus is still here. Yeah, it belongs to the products. So don't forget the sign. Right, So we add up the we do minus 486 minus 137, and we get minus 1856 equal to the products. Right, we have a total of 4 products, yeah? 4 OH bonds. So we do minus 1856 divided by, we still have a minus, so 4. And because there are 2 negatives, the answer becomes positive. So we have positive 464, which is C. And so the answer is C. Hydrogen gas can be produced as shown below. Which conditions produce the greatest equilibrium yield of hydrogen? So hydrogen is in the products, and we have temperature and pressure as the reactants, right? So if it's delta positive, it's endothermic. So to get more products in an endothermic reaction, you increase the temperature. And so we will go for C or D, because A contains low temperature. If this was exothermic, then we would go for A or B, but it's endothermic. Right. And now we need the pressure. So the pressure, we use the gas states that are available. So once we increase the pressure, equilibrium position will move to the side of less pressure. Or if you decrease pressure, it will move to the side of equilibrium will move to the side with the highest pressure. And so we've got the highest pressure is on the products side, which has the hydrogens. And so that would mean that we need to decrease the pressure, because if we decrease the pressure, then equilibrium will go to the side that has the higher gaseous states. And so we have a total of 4, because 3 plus 1 is 4, and here we have 1 moles of CH4 and 1 moles of H2O, and so that's 2 and that's 4. And if we decrease the pressure, then equilibrium will go to the side that has the highest number of gaseous products to make up for the loss, and therefore the answer is D. The reversible reaction below is in equilibrium. So that's SO2 plus O2, you get SO3. The equilibrium concentrations are shown in the table, as shown here. What is the numerical value of Kc? Okay, so Kc is products over reactants, yeah? And the the ratios they're given in will be what's written outside the bracket. So if we go products of reactants, the product is SO3, and SO3 here is 1.44, and so we put 1.44. But because it has a ratio of 2, we're going to put 2 outside the brackets. Under it, put the reactants, and the reactants is SO2, which is 4, and it has a ratio of 2, so we're going to put 2 on the outside bracket, multiplied by the other reactant, which is O2, and we have 2.4 here. Molecular ratio is 1, and so we get 2.4 with nothing on the bracket, so just 1. And we put that into a calculator and we get 0.0540, making the answer B. Okay, which statement is correct for the 2 structures below? Right, so this is what we're given. They have the same empirical formula, right? So empirical formula, we determine that from the molecular formula, and we keep breaking it down to its to the most simple empirical formula we can get. So if we count all the carbons and the hydrogens on this side, we have C10H20, and if we name this structure number 2, and we add up all the carbons and hydrogens, we get C10H20, so the same MR. And that would mean that B, they have different relative molecular formula, so relative molecular masses, which is the MR. That's false, because they have the exact same MR, and so B is wrong. They are structural isomers. Well, they're the exact same shape if you look at it. You just have to, if you just flip this on top, and we just look reversed, flip the whole thing, then we get the same structures on both sides. Because if we look at this end, it's the same thing to this end. If we look at this, the same thing to this. They're the same structure, they've just been played around a bit with, and they haven't changed. So that's just flipped upside down. So is this. So you're not really changing anything to make it an isomer. And so C is wrong. They have different functional groups. No, they contain the exact same functional groups. They have a double bond between carbon here, and they have the exact same functional group. So that means just this double bond. That's it, and they both have it. And so D is wrong. And so you have the same empirical formula. And so because it have the same MR, therefore the empirical formula will also be the same. And so this is how you calculate it. So C10H20, you half that, you get C5H10. You half that, so you divide it by 5, you get C5H5. So this is the most simple ratio you can get. And because they have the same MR, they'll have the same empirical formula. Which property explains the low reactivity of alkanes? Okay, so low reactivity means that the molecule is highly stable. And they're stable because of the bonding. And so you're going to need to put a high amount of energy to break that bonding, to break that stability. And so if we take a look at the options over here, we have electron pair repulsion between the sigma bonds. Well, no, if there was electron pair repulsion, in high amounts of electron pair repulsion, you would have a high reactivity because the structure will not be stable. And so A is wrong. Free rotation about the sigma bonds, yes, but that does not have an effect with reactivity. It would if you had a double bond, and that wouldn't be with sigma bonds, and that would be in alkenes. High carbon-to-carbon bond enthalpy, well, yes, because bond enthalpy is the energy needed to break the bonds, and if they're stable, that means they'll have low reactivity, and so C is the correct answer. High polarity of the CH bonds. We know CH bonds are not polar. Yeah, so once again, they don't contain nitrogen, oxygen, or fluorine, and carbon is not polar. It will not have enough electronegativity to take the electrons away from hydrogen to give it the delta positive and delta negative effect. So the answer is C. What are the correct reagents for the conversion below? Okay, so we have this, and it's turning into this. The only thing that changes is we go from an OH to a bromine. So this is what we call a substitution reaction. Yeah, not an addition reaction. An addition reaction usually happens when there's a double bond, so when you're adding products in without taking anything out, unless the double bond is being broken. So you usually add Br2, so you get 2 bromines attached, or you get HBr, so you have a hydrogen bromine being attached. But here we have one group being removed and another group coming to take its effect, to take its place. So that's a substitution reaction. And it's happening with bromine. But is it Br2 or NaBr? Br2 happens with addition reactions, and both bromines will attach. And NaBr will happen in a substitution reaction. And since this is a substitution reaction, then it will not be Br2. So automatically A and B are removed. Now, we're left with either sulfuric acid or sodium hydroxide. Right, so that's an acid and that's base. We know that for substitution reactions, we need a catalyst, and the catalyst here will be an acid catalyst, and therefore it will not take part in the reaction, and hence we don't see sulfur here anywhere, but it will help the reaction, and so the answer is C. Which compound could react with both potassium dichromate and sulfuric acid is the catalyst here, an oxidation reaction, and an acid catalyst, so again, sulfuric acid in the elimination reaction, right? So this one's probably the easiest one, the top one, and potassium dichromate, whenever we see that, that's an oxidation reaction, as mentioned here. And oxidation happens only in primary and secondary alcohols. Primary alcohols will turn into aldehydes and then carboxylic acids, whereas secondary alcohols will turn into ketones. And so automatically anything with a tertiary alcohol is removed. So if we skim the list, so this is a secondary alcohol because the alcohol group is connected to a carbon that's connected to 2 carbons, so secondary. Here we have the alcohol group is connected to a carbon that's connected to 2 carbons, so secondary alcohol. Here we have an alcohol group that's connected to a carbon that's connected to 1, 2, and 3 carbons. That's tertiary alcohol. So we know that's wrong. We can just get rid of this. And here we have D. So we got 2 alcohol groups. So we have the alcohol here group is attached to a carbon which is attached to one carbon only, so that's the primary alcohol. And once again, we have an alcohol group attached to a carbon that's attached to one carbon. Remember, you determine what type of alcohol it is not by what carbon it's attached to, but the carbon itself that's attached into how many carbons is that attached to. So not the first carbon, but the second carbon. Yeah, so it's the carbon that's basically adjacent to the alcohol group. So we've done that. Now, an elimination reaction. Whenever we have an elimination reaction, we form a double bond. And elimination would mean that we have a removal of water. And we would take the alcohol group as the OH, and the hydrogen would come from an adjacent carbon. And in place, we would have a double bond. And so if we look at number A, and what would happen is OH would be gone, and we would form and H would be gone, and we would form a double bond here. Let's see if that works. Because the H is gone, we removed that bond, and we've removed that bond. Because remember, carbon can only form 4 bonds. So if you want to create a double bond, if it's going to have more than 4 bonds, it will not work. So let's see, this carbon will have 1, 2, 3, and 4. So that works. And this carbon will have 1, 2, 3, and 4. So that works. So that would mean our answer is A. But let's go through the rest. Right, now let's do this one. Automatically, we can't use any carbon here. Because yes, we'd remove the OH, and we go, okay, we need to remove a H. Well, this one has 1, 2, 3, 4 bonds, so this carbon is useless. Now, let's take a look at this carbon. Once again, 1, 2, 3, 4. There is no room to create a double bond, so that's why it's not B. Now let's go to D, primary alcohol. So we're going to remove the OH here, and we're going to remove the H here. So yeah, we can form a H2O. However, if this is gone, we need to form a double bond. If we try to form it here, we're going to have 1, 2, 3, 4, and wait, there's another bond here that we're going to form. That's 5 bonds. It will not work. And since it's symmetrical, then the same thing will happen over here. We're going to remove the OH group, and we're going to remove the H, and we're going to be left with this. That's already formed 3 bonds, so that's 3, and the fourth one already exists between them, and you're adding another bond to create a double bond. That's 5 bonds, and hence it will not work. That's why the answer is A. A student reacts 24.24 grams of 2-bromobutane in the reaction below, so here. The reaction produces 4.81 grams of this. What is the percentage yield of this? Okay, so percentage yield is actual mass over theoretical mass times 100. Right, so do we have the actual mass of this? No, but we can get it. Do we have do we have the theoretical mass? No, we do not. Do we have the actual mass? Yes, because it says the reaction produces this much. That is the actual. Whenever you see the reaction produces and it's 4.81 grams, that's the actual mass. So we have the top bit ready. We have that. Now, theoretical mass. That's how much you're going to predict will happen. And you calculate this from the reactants. So do we have the mass of the reactant? Yes, it tells us 24.24. Do we have the MR? Yes, they've given it to us. Therefore, we can work out the moles. And so mass over MR gives us moles, so that's 0.177. And the thing is, it's a 1-to-1 ratio, because if it's not, they would have told you it's not a 1-to-1 ratio, and because, you can add it up and to see if they're 1-to-1 ratios, but in these type of questions where it's only 1 mark and they've already given you the MR, there's also going to be a 1-to-1 ratio. So that would mean that the number of moles that we have here will be the same for the number of moles here. And so that would mean we have the moles, we have the MR. Using this, we can calculate the mass. So we tie them together and we get a mass of 13.1 grams. That's the theoretical mass that we should be getting. When we actually did the reaction, we're getting 4.81, that's 2 waste products. And so we have 4.81 divided by 13.1 times 100 gives us 36.7. That would be the percentage yield, and this is C. So the answer is C. Which row describes a nucleophile? Okay, so a nucleophile, also the opposite of electrophile, and this is something you just have to know. So, or if you don't know a nucleophile but you know the properties of an electrophile, then it'll be the exact opposite. So, for example, we know that electrophile is an electron acceptor, and so a nucleophile will be an electron donor. And we know that electrophiles are attracted to places of high electron density, and so a nucleophile would be attracted to places of low electron density, and so that would mean that the answer is B. So, final question. The mass spectrum of a carboxylic acid contains peaks at MZ29 and MZ102. Which compound could have produced a spectrum? Okay, so the first thing you see is you have to determine the peaks. And the first thing I would do over here is always work out the MR, because it really helps a lot. Because if we work out the MR, we can say this is 102, so that causes that peak, and this is 102, and that would cause that peak. But we don't have 102 from B and D. We only have 88 is the maximum number of the MR, and so it cannot be 102, and so it cannot be B and D, and so it just eliminated 2. Now 29. This basically means that we just have to start breaking up the compounds and see, can we get an MR of 29? If we do that, and we break it up from here, we have C, and we have C, and we have C, and we have 3 H's here, 3 H's here, and 1 H here. That's not going to be 29. And so that won't work. Once again, if you break this up from anywhere, any side, you will not get 29. Moving on to here, if we choose to break over here, we're going to get carbon here, which is 12, and a carbon here, which is 12. That's 24, and that's 3 hydrogens over here attached to the carbon, and 2 hydrogens attached to the carbon. If we add that up, that will give us 29, and therefore the MZ peak was actually caused by this CH3 and CH2, and so the answer is C. And so that's it. We finished section A.